let's look at phosphate here. So here we've got phosphorus and 4 oxygens. And like we just mentioned with H3O+, sometimes we're not sure who do we put in the middle and who do we put around. One of the guidelines is that more electronegative elements tend to be in the terminal positions, so around the outside. Another thing that often happens is that the molecules are symmetrical. And so here we have 1 phosphorus, so that's going to be in the middle and the 4 oxygens around it. So I'm going to start out like that. And then I need to think about, well, how many valence electrons do I have to work with? So I've got 1 phosphorus with 5, and I have 4 oxygens, they each have 6, and then the -3 charge means I have to add 3. So that's what, 32? It's always a good idea to double check. Yeah, 32. So I already have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And we want to say, yay, we're done. Except we're not done. Oops, not that one. We do need to put brackets around this and indicate the charge on the outside. But we need to check the formal charges. So if I look at this phosphorus in the middle, the phosphorus brought 5 electrons to the molecule, or to the polyatomic ion. So it brought 5, and it's leaving with 1, 2, 3, 4. So that's a positive 1 formal charge. That doesn't look like a plus. So I'm going to just back that up, clean that up, and say this is +1. And then we can look at, well, what are the formal charges on the oxygens? The oxygens all have the same situation where they have 3 lone pairs and a single bond. Oxygen brings 6 electrons in, and here it's leaving with 1, 2, 3, 4, 5, 6, 7 electrons. -1. So this has a -1 formal charge, -1, -1, -1. Now, the formal charges do add up to the overall charge, but everybody's got a formal charge. And we should be looking for trying to get everybody to 0 if possible. So here we've got a situation where we've got a positive formal charge and a negative formal charge, and so we can probably do some moving around and get both of those to 0. So the oxygen here has extra electron because of its negative formal charge, and the phosphorus is short an electron. So what we can do is take a lone pair from the oxygen and make a double bond with the phosphorus. This oxygen still has its octet. Now phosphorus has 10 electrons, but phosphorus is in period 3, and so it can handle that. Now if we look at formal charges, for this oxygen, it came in with 6, and it's leaving with 1, 2, 3, 4, 5, 6. So 0 formal charge. And the phosphorus came with 5, and it's leaving with 1, 2, 3, 4, 5. So that's 0. So that's better. So these guys each have a -1 formal charge, but now these two are both 0. So we're looking for lowest overall formal charges. So when we go over here to the formal charge box, for phosphorus, we're going to write 0. And we've got oxygen 1 and oxygen 2. There's 2 different kinds of oxygens. You can call these guys 1 and this one 2, or the other way around. I don't care, but there's 2 different kinds. Some of them have a -1 formal charge, and some have 0. You do not have to show the formal charge over here. You can, but it's only required over here.
So for in molecular geometry, how the double bond would count as 1 electron group, for something like this, it would be 2 bonding pairs, right?
Yeah, so number of bonding pairs on this worksheet, that would be 2 bonding pairs. And then here's a bonding pair, and here's a bonding pair, and here's a bonding pair. So 1, 2, 3, 4, 5 bonding pairs. I want to get this worksheet so that bonding pairs and electron groups matches up better, but I don't think there's a way to do that. But here's the number of bonding pairs, and then lone pairs, we're only interested on lone pairs in the central atom, so this phosphorus has 0 lone pairs.
So then that won't make too much of a difference with our initial question of the molecular and molecular geometry and the electron geometry, because the lone pairs comes back to 0 in this one.
Yeah. For this one, you'll end up with the correct geometry even if you've got your electrons in the wrong place.
Right. So with 4 groups, how are we going to name this just by looking at this?
Well, how do 4 groups arrange themselves?
Okay, so it seems like it's going to be, those are the 4 bonding groups, not electron groups, right?
Well, there's actually 5 bonding pairs of electrons, but in terms of chapter 11 and electron groups, this is 1 group.
Right.
It's 2 pairs, but it's 1 group.
So
1,
4.
2, 3.
So 4 electron group or 4? No, that's 4 bonding group.
It's 4 electron groups.
And then the bonding groups is also 4.
Well, in this worksheet, we're talking about bonding pairs. A pair is 2 electrons.
Oh, I'm trying to name it with the next chapter as far as the electron group and bonding group to get by looking at a Lewis structure to try.
Well, so you look at the electron groups as 4, and you name the electron geometry.
Okay, so electron group 4. I'm looking at the table 11.1 in your thing. So electron group is 4, and then the bonding group.
No, don't do it like that. So let's go back. Hopefully I won't lose that. So let's go. Oh, that's the wrong one. Let's go back to this. Okay, so this is what you've got, right? We have 4 electron groups, 3 single bonds and a double bond. So don't look at the table. Name it. What shape is this?
So something to do with tetra.
Mm-hmm. Tetrahedron.
So tetrahedral.
Tetrahedra. Mm-hmm. So that's our electron geometry. And then instead of talking about bonding groups versus non-bonding groups, ask yourselves, are there any lone pairs? Are there any lone pairs here?
No.
No. Then it's just the same. If one of these was a lone pair, instead of looking at the table and getting confused by all the permutations, if one was a lone pair, let's make one a lone pair. So I still have 4 groups, right? So the electron geometry is still tetrahedral. But when I talk about molecular geometry, I make that one invisible and describe the shape that's left. And that is, it's triangular, but it's not flat. It sticks up, so it's a trigonal pyramid. I think that's a much better way of thinking about it, because it's based on understanding rather than following a set of rules or looking at a table and trying to figure it out.
Yeah.
So let's see if I can go back to what we were looking at. I think I can get that back. Come on. Magic. Okay. So the one thing we didn't finish on here was resonance. Are there resonance structures, and if so, how many? This one, yeah, there are. This one, we've got a double bond here and single bonds here. And so if you think of these as, being like children, and each bond is a cookie or something, why does this guy get 2 cookies and the other guys only get 1, right? There could be a big fight about that. Well, the truth is, it isn't one double bond here in these single bonds. They're all kind of mushed together as resonance structure. And so this, well, actually I can't do it that way. It's too much moving around. But this double bond can be here, or here, or here, or here. So that's a total of, total of 4 resonance structures. Because while these oxygen atoms are all the same element, they are individual oxygen atoms. If you think about people and you think about a set of quadruplets, right? They may look the same, they may be identical, they may have the same genetic makeup, but if you talk to them, they are different people, and they'll get really upset if you think that they're interchangeable, right? So
that PO43 minus will be a tetrahedral?
Mm-hmm. Yep.
Okay.